Hi! In the last video, we were discussing derivatives of exponential and logarithmic functions. Now, we're going to start using them to different problems. We will still maintain at the beginning mostly a very descriptive stage, but as we will go, we will get into more and more typical economic problems. Okay, so look, first let's introduce some new category we haven't had before, although you have already seen it. Let's say that V equals AERT. Okay, we already seen those expression, but look, from now on we will call V future value. Why future value? Look, we can think about this entire problem in a following manner. At the beginning, you have some amount of money, A. You put it into a bank, and the amount of money you've got grows. And it grows, of course, exponentially. Right? We know that this function is increasing faster and faster. How can we check it? Well, we'll see in a second. Now, if I would ask you, now, what is the growth rate of this function? Well, we would have to calculate growth rate at each single point over here. Why? Because here we are discussing continuous time. So we can actually check what is the growth rate of this expression every single moment. Okay, so let's do it. Now, first thing we need to do is to define growth rate. And look, instantaneous rate of growth, so rate of growth that happens at every single moment, we will define as, let's just say, g of v for now, and this will be derivative of v over v. Why this expression? Look, derivative over here is telling us by how much value of the function changes when the argument time changes by some infinitely small amount. And here we have a total function. So basically what we are obtaining out of this is a percentage change in the value. Because we will know by how many percent a given function grows every possible second. And look, let's do it for the function that we've got. Okay, so first thing, we probably have to calculate derivative. Of course, derivative with respect to time. This is an exponential function, so all we've got to do is to calculate derivative of this and put it up front. So look, what we are getting here is simply R, A, E, R, T. Right? Now, I can simply substitute my result over here. We know that v prime, so the derivative is r, a, e, r, t, while v is a, e, r, t. Those two cancel each other out. We get r. This result might seem a little bit surprising because we know that this function grows exponentially, but we get rate of growth that is constant. So maybe we should make sure that this function definitely grows faster and faster. How can we check it? We can use second derivative test. If first and the second derivative is positive, we can be sure that the function is increasing and it's convex, which means that it has positive acceleration, increases faster and faster. So let's calculate second derivative over here. Look, assuming that A is positive, R is some interest rate, which is also positive, this definitely needs to be a positive number. Now, if I calculate the second derivative, again, all I have to do is to differentiate this with respect to time. I'm getting this. Again, this is certainly positive. So, what we see from that is that this function grows exponentially, but it has constant growth rate. Okay, let's check it. Maybe let's use a different method of finding it. Look, V equals AERT is a function that can be easily logarithmized, right? So if I'm logarithmizing this function, I'm going to get ln V equals ln A plus RT ln E. But of course, at this moment, we remember very well that ln E is simply 1. So we can eliminate it. Okay, now, if I differentiate this with respect to time, what am I getting over here? Look, here, we've got a function of V, and V is a function of time. So here we need to use the rule and look, right away we will obtain V prime over V or simply growth rate of V. And again we see that it's equal to R. Okay, so we've used two different methods and we've obtained the same conclusion. So, on one hand, we see that this function is growing faster and faster and faster. On the other, we see that the growth rate of this function is positive. It is constant. So, how can we reconcile those two facts? Look, actually, the reason behind this is very, very simple. And I'm going to use a very simple example to show this to you, but in a discrete time. What discrete time is, we will be discussing in a second in detail, but I think you can glimpse from the context. Look, imagine now that you have $100 and interest rate in a bank is 10% or simply 1/10, right? Which means that if you put this money for 0 years, so you didn't put the money, you are having $100 at the beginning. Now, let's say that, let's see what happens if you put this $100 into a bank for 1 year. Well, of course, this is very simple. All we would have to do is to take this $1, 1 plus interest rate, which is 1/10, to the power of 1, because we put it only for 1 year. We get that this is $110. Okay, so how much money will we have after 2 years? Well, if we want to check after 2 years, we raise it to the power of 2. And this is how much money we will have after 2 years. Now, how much money will we have after 3 years? Okay, now numbers are getting pretty and present, so I'm going to use the results. Still, this was calculatable. Okay, and let's just check two more to see the pattern. Okay, so after 4 years, we would have $146.41. Okay, and the last one, after 5 years, we will have $161.051. Okay, so what do we know about this example? Look, in this example, we definitely have A. This is our A, right? We've got growth rate, R, and we see that this growth rate is constant. So, it means that each year, the amount of money we've got increases by the same percentage. Okay, but look, those increases, you see that the numbers we are getting bigger, but not by the same amount. Look, first, we can say the delta here was $10, right? From 100 to 110. Then delta grew to $11. Then delta grew to $12.01. Then over here, delta grew to $13.31. And finally, delta has grown to, okay, I'm going to check this one up to $16.105. Okay, so what do we see over here? Look, even though the percentage increase is constant, it's always 10%, we see that actually the amount of money we are getting each single year is getting bigger and bigger and bigger. Why is that happening? Because look, we have capitalization. Capitalization takes place every year. If it takes place every year, it means that after the first year, we have $110, and we calculate this additional 10% for this amount of money. Then, after 2 years, we have $121, and we calculate additional 10% for this amount of money. So look, what is changing here is the base, based on which we are calculating the percentage increase. So look, because even though the rate of growth in terms of percentages is the same, is constant, then because we have bigger and bigger and bigger and bigger base, then we will see that those values are increasing by a bigger and bigger number. And look, this is exactly what we see in this graph over here. Look, even though the growth rate here is constant, the amount over here is growing by a bigger and bigger number, because 10% out of $100 is $10. 10% out of $110 is $11. Out of $121 is $12.1. And this is why this function actually is going faster and faster and faster. Okay, so now that we reconcile those two facts, let's go back to the growth rate we calculated. Look, this one, they are all the same, but look, you see that if you want to actually calculate growth rate of some function, the best way to do it is to logarithmize the function and then differentiate, because we will always obtain this expression on the left-hand side of the equation. So we will obtain away. And look, in this case, we call this particular growth rate instantaneous rate of growth. Why do we call it like this? Well, because this one is based on derivatives, not on differences divided by the base here. But look, this is giving us the exact rate of growth at each possible point over here. Okay, and look, the other thing that we should notice from this example is that it was really convenient to use logarithms here to calculate this growth rate, right? And this gives us another point on which we should concentrate a little bit, and this is how would look the graph of this function, right? Look, basically what we've got here is that if I'm going to take this function and I'm going to logarithmize it, I'm going to obtain this expression, right? So why not put this expression in the graph? Here we have t, here we have ln v. Okay, and look, if time is 0, we can read on this v, ln v is equal to ln a. So this is the natural logarithm of the initial sum of money that we have. And then what is happening? Look, r is constant, so this is just the coefficient for r. We are getting simple logarithm, a simple linear function. And look, for this reason, very often it is better to use this scale that you see over here. We call this semi-logarithmic scale. The advantage of it is that it changes exponential expressions into linear functions, and in general, the slope of this function, so tangent alpha, which at a given point, which is also equal in this case simply to d d ln v over d t, as you see, is equal to growth rate of this function. So what we see over here is this is how this function is growing, but also each point informs us about the growth rate. So if we would compare two functions, you would have some ln c that is going like this. We could see that this function is growing faster. It's characterized by higher growth rate. And of course, we could have a function, if it turns out that the function, for example, looks like this. What we would see here, we would have variable growth rate. You see, at the beginning, the function grows really slow, then it starts to grow really rapidly, and then the growth stabilizes. Okay, so I think this is it. Oh, maybe one more thing. There is another way of thinking about instantaneous rate of growth. Because look, derivative in economic terms, we usually think about it as marginal function. And v is simply a total function. So we can also think about instantaneous continuous growth rate as a ratio of marginal to total function. Okay, and look, thus far we were concentrated only on continuous time. Continuous time more or less is the time how it is in reality. Reality do not work in some point of time. We continually exist until we die, and we can feel the time happening every second, right? But when you go to a bank, they will not give you, the capitalizations will not be happening every second. You will go, you make a contract whether your capitalization should be on annual, semi-annual or quarterly basis, or monthly basis, depends on the financial instrument you are going to use. So, in various applications, and especially as you will learn in the future in empirical application, it is better to use discrete time. Look, what does it mean, discrete time? Discrete time means that time, we are not noticing time at every single moment, but at some regular periods. Look, it's really easy to explain over here. Here we have a function, so future value of A. Look, because A is the amount of money we have at the beginning, we put the money into a bank, and it grows, right? But let's just say that we have exactly, that we know this function, how it would look at every single moment. But our bank adds interest every year. So, how would we see it if I would collect the data on 4 years and would like to see how the amount of money we will have 1 year from now, 2 years from now, 3 years from now, and 4 years from now look like? Okay, look, if the time would be 0, we are still at $8, right? So we would be here. Then, after 1 year, we would have this much money, 2 years, this much, 3 years, this much, and 4 years, this much, right? Look, we would not see anything that was happening in between, because look, bank adds you interest, let's just say the last day of the year, bang. You could also think about it that your amount of money was this much, and then it grew to this point. It was this much the entire year, grew to this point. This much the entire year, grew to this point. But actually, what we need to see over here are only those dots that you see. Okay, now, if we have defined what is discrete time, how will things change in terms of calculating the future value of some amount of money A we've got? As it turns out, we kind of already did it, even without knowing it, because usually this is more natural thing to think about compounding interest on some amount of money in terms of a discrete time. Well, because if this is the future value defined for continuous time, then if I want to find future value of some amount of money A, what do I need to do? Well, I need to add 1 plus interest rate. Look, from this moment on, I know that from macroeconomics usually nominal, real interest rate. For us, from this moment on, I is discrete interest rate in discrete time, R is interest rate in continuous time. and I times t. This is exactly what you saw on this blackboard a couple minutes ago when I was calculating how much money will you have after a year, after 2 years, after 3 years, and so forth. So look, those two formulas actually look kind of similar, right? So is there any direct relationship between them? Well, as it happens to be, there is. Because look, it turns out that you can always find a function with e that will give you exactly the same points as this one. Now, how can we calculate it? Look, basically, what we want is to equalize those two functions. So we want them to give us exactly the same values. Now, we clearly see right away that we can get rid out of a, right? So we divide both sides by a. Then the second thing I'm going to do is I'm going to take both sides of this equation to the power 1 over t. Right? So, as a result, t times 1 over t, it gives us 1. E to the power of r is equal 1 plus I. Okay, so now we've got some relationship, but this is not what we want. We cannot directly substitute, unless, of course, we take natural logarithm of both sides. So we will have r times ln e, but again, ln e is just 1, and we get that this is equal to natural logarithm of 1 plus I. So, this example actually shows us that it is indifferent which approach we are taking, and in real life examples, when you go to a bank, you will be dealing with some form of this formula. But in our economics examples, we like everything to be continuous because then we can calculate derivatives, right? We can actually find every point, every optimum. So in our applications, we will be using continuous time. But look, we've learned that v, so future value, can be calculated as a 1 plus I to the power of t, which is equal to a to the power of e times e to the power rt, where r is equal to ln 1 plus I. Okay, so at this moment we know how to discount, how to transform one base, how to go from discrete to continuous time, and in the same way in the opposite direction. Okay, but look, what have we been talking about so far is future value. Future value means we have some amount of money, A, and we put it into a bank, we invested in something, and we, based on the function we've got here, we are able to obtain what will be the value of our amount of money, let's just say, in the future, right? But this is not the only problem you need to deal with when you're thinking about money. from a completely different perspective. Imagine that you've got a question. Would you prefer to get $10,000 today or $10,000 1 year from now? Well, I hope for everyone the answer is obvious. I want it now. But is there any rational reason why we would prefer to have this money right now? Well, look, if I have $10,000 today, I can do something with it, and because of that, have more than $10,000 1 year from now. It's obvious. Look, if, for example, interest rate is 10% at a bank, I'm getting $10,000 today. It means that after a year, I'm going to have $11,000. So, every time when we are considering some value that we are going to receive in the future, we actually need to take this into consideration, right? And look, this brings us to the topic of discounting. Discounting and negative. Okay, so look, we clearly seen that it is better to get the money earlier than later. But look, probably if you would be asked a different question, what would you prefer? To get $10,000 today or $10,500 1 year from now? $10,500 1 year from now. Well, in this case, you could actually, this time, you should think about it before you say, I want $10,000 today, because you should weigh your options. And look, going back to this example, if interest rate is 10%, then it's still better to get $10,000 today, because if you put money into a bank, you will receive $10,500, $11,000, and you are offered $10,500. But if somebody offered you $12,000 1 year from now, we'll clearly see that it is bigger than the amount of money we could get in a bank if we put the money under this interest rate. So in this situation, the rational thing to do would be to wait 1 year. Right? Of course, we are taking every other considerations aside just to make things clear. Okay, so this is telling us that in our investment decisions, we should take into account interest rate, right? Now, so how do we do it? Okay, look, let's just say that over here we will have discrete time, and over here we will have continuous time. Maybe that. Okay, so let's start with what we already knew. So, future value. We know that if I want to know how much do I have out of $8 with interest rate I will use this formula for future value in discrete time. And I can use this formula in continuous time. Now, the trick is how to measure the value of some amount of money we are offered to get in the future. And look, just as here we had some amount of money A at the beginning, and we were calculating the future value, now we are being offered some amount of money in the future, so we need to take it into present terms. So we will be calculating present value. And how do we do it? Look, it's actually quite easy. Look, all I have to do, if here I was multiplying by this exponential expression, as well as here, all I gotta do is to divide now. And look, I will obtain, if I divide both sides by this, I'm obtaining that A is equal to 1 plus I to the power, is equal to V over 1 plus I to the power of T, or simply V 1 plus I to the power negative T. And here we will have a very similar situation. A will be equal to V over E RT, or simply E V times E RT, but with minus up front. Okay, now look, both of these expressions we will call discounting factors, or discounting factors. Okay, before we go back to what we already said about economic interpretation of present value, let's see this on the graph. Let's see it on the graph. And again, I'm gonna start with continuous time, and then I'm gonna show you how it looks in discrete. Okay, look, now on this axis we've got A. Because look, V this time is some amount of money you are promised to get in the future, right? But look, if this future would be 1 second from now, so we would say basically no time has passed. No time has passed. Then this V would be worth to you its nominal value, right? If V is $100, you're receiving right now. But look, it's very rational to think that the longer you need to wait to receive V, the lower should be the value of V. And look, let's see how this works. Look, we know that e to the power rt is an exponential function. And as time passes, this gets bigger and bigger and bigger and bigger. So in here, we are dividing V by a bigger and bigger and bigger number. So look, as a result, the value of V, so the promise of receiving money in the future is getting lower the more time needs to pass before you receive this exact amount of money. And look, okay, now, so how would we see this in a discrete time? Well, you can probably guess, not much problem here. 1, 2 years, 3 years from now, 4 years from now, and so forth, right? But, so what is the economic interpretation of that? Look, we always need to think about the opportunity cost. This discounting factor eliminates or accounts for opportunity cost associated with putting money into financial instrument or putting simply money into a bank given interest rate R or I. We will be concentrating on this, so R. And look, the higher is the interest rate, the higher is the opportunity cost of receiving money later. Because look, if you're considering if you want to get $1,000 today or 1 year from now, then of course, if interest rate is $5%, then if you're not getting money today, you're gonna lose $50. But if interest rate is 20%, you're gonna lose $200, which of course is the worst option. And now, the second thing we need to take into consideration is the passage of time. The longer you need to wait, the more capitalizations you could have taken advantage from, and the more money you could make. And look, I hope this shows you that this such simple manipulation with the location of this factor actually allows us to, on one hand, calculate future value of some amount of money we have now and present value of some amount of money we are supposed to obtain in the future. Okay, so I think this was lengthy enough. In the next video, we're gonna do we're gonna take care of growth rates and elasticities. Okay, take care.